Welcome to lecture number 5. In this lecture, we are going to continue with our earlier lecture number 4. In earlier lecture, we had obtained the parameter estimates of beta 0 and beta 1. Keep in mind that we had 3 parameters, beta 0, beta 1 and sigma square, and out of them sigma square is still remaining. But before that, we would try to investigate the statistical properties of beta 0 hat and beta 1 hat. The reason is as follows. The parameters beta 0 and beta 1, they are the values in the entire population, and we do not know. We have tried to estimate them on the basis of a given sample of data. So, how to ensure that the values which are being obtained using beta 0 hat and beta 1 hat, they are good values or bad values. So, we try to expose them to the statistical properties, and we try to see whether they satisfy some statistical properties or not. So, if you try to recall, our model was y is equal to beta 0 plus beta 1 x plus epsilon, and we had obtained the observation, say xi yi, I goes from 1 to n, and we had obtained beta 1 hat as say sxy upon sxx, and beta 0 hat was obtained as y bar minus beta hat 1 x bar. Just for your remembrance, this sxy was summation xi minus x bar, yi minus y bar upon sxx, which is summation xi minus x bar whole square, and all the summations are going from 1 to n. Now, let us try to investigate the properties. Properties of beta 0 hat and beta 1 hat. Okay. So, one thing we can see here that both beta 0 hat and beta 1 hat are the linear functions of y. What does this mean, and how I can show it? So, let me try to take it here, say here beta 1 hat. Beta 1 hat here is given by summation see here xi minus x bar, yi minus y bar upon summation xi minus x bar whole square. So, this I can write down here summation say xi minus x bar times yi divided by summation xi minus x bar whole square minus summation xi minus x bar and times y bar. So, y bar is independent of I, so I can write down over here, and this becomes summation xi minus x bar whole square. So, we know that summation xi minus x bar is always equal to 0, I goes from 1 to n. So, this term becomes 0. So, now you can see here that this is now only here a function of yi, and so I can write down here it is a summation I goes from 1 to n, say xi minus x bar upon say here sxx times yi, or I can write down here I goes from 1 to n, say ci yi, where your ci is xi minus x bar upon sxx. So, I can show that this beta 1 hat is simply a linear function of yi. One question crops up that why I am emphasizing on the linearity of the estimator. You see, in this model we have epsilon as a random variable, and because of that y also becomes a random variable. later on we will see that when we try to find out the expectations or variance and other statistical properties over beta 0 hat and beta 1 hat, then doing mathematical manipulations over a linear function is easier than doing it on say any other non-linear function. So, that is why if my estimators are linear, the algebra and further properties become simpler to derive. So, that is the advantage of having a linear estimator. Similarly, I can also show here that beta 0 hat is also a linear function of y, which is not difficult to show, right. And this can also be shown say directly from this equation. You see, y bar is nothing but a linear function of y1, y2, yn, and beta 1 hat we already have shown that this is a linear function, and x bar is a fixed value, that is a constant value, that is a non-stochastic value. So, again the linear combination of the linear combination is again a linear function. So, it is not difficult to prove that beta 0 hat and say beta 1 hat both are the linear functions of y. The next property what we try to investigate here is about the unbiased character of beta 0 hat and beta 1 hat. Just for the sake of review, I can explain you what is the property of unbiasedness. So, if I say, if I have here a random variable say x, which is following a probability density function say here fx theta, right, and when we try to estimate theta by some estimator theta hat, so we say that theta hat is an unbiased estimator of theta when expected value of theta hat is equal to theta, right. So, now if my question is I want to see whether beta 1 hat or say beta 0 hat is an unbiased estimator or not, then essentially we have to see whether expected value of beta 1 hat is equal to beta 1 and expected value of beta 0 hat is equal to beta 0. So, let us try to attempt on it. So, okay. So, now we have considered this beta 1 hat as say Sxy over Sxx, and in the earlier slide I had shown you that this can be written as summation I goes from 1 to n Ci yi, right. Okay. So, when I try to take its expected value of beta 1 hat, this becomes I goes from 1 to n Ci expected value of yi. Now, the question is what is expected value of yi? So, let me try to solve it further. I goes from 1 to n say Ci, and expected value of yi is nothing but your beta 0 plus beta 1 say here xi plus epsilon I. Okay. So, this becomes I goes from here 1 to n Ci, and this becomes here beta 0, because expected value of beta 0 is the same as beta 0, because beta 0 is a constant, that is a fixed value, and this becomes beta 1 expected value of xi, which is again xi, because we have assumed that xi is a non-stochastic, and then it becomes say expected value of epsilon I, and expected value of epsilon I we have assumed that this is going to be 0, right. So, now if you try to open it, this becomes beta 0 summation I goes from 1 to n Ci plus beta 1 times summation I goes from 1 to n say Ci xi, right. What is the value of summation Ci? So, summation Ci, if you try to find out here, this comes out to be summation xi minus x bar over Sxx. So, this is going to be 0. So, the summation of Ci, this is actually 0. Let us now try to obtain the value of summation Ci xi. So, this can be written as I goes from 1 to n xi minus x bar upon sxx times xi. So, this can be written as summation xi square over sxx minus summation I goes from 1 to n xi over sxx. So, summation xi is nothing but n times x bar. So, this quantity can be written as summation xi minus x bar whole square over sxx, and this quantity is again ssx upon sxx, which is equal to here 1. Right. So, I can write down here that expected value of beta 1 hat, this is equal to now here beta 0 into 0 plus beta 1 into 1. So, this is equal to nothing but beta 1. So, this implies that beta 1 hat is an unbiased estimator of beta 1. Right. So, now we have a reason to be happy that the estimator that we have obtained on the basis of principle of least square by using the available observation, this turns out to be an unbiased estimator. Right. Okay. So, next we try to find out whether beta 0 hat that we had obtained as y bar minus beta 1 hat x bar, whether this is an unbiased estimator or not. So, we try to find out its expectation. So, expected value of beta 0 hat, there is nothing but your expected value of y bar minus beta 1 hat x bar, and so if you try to rewrite it, y bar is nothing but beta 0 plus beta 1 x bar minus beta 1 hat x bar. So, this comes out to be again beta 0 minus x bar expected value of beta 1 hat minus beta 1, right, because we had assumed that that xi's are non-stochastic. So, x bar is again a fixed quantity, right. So, we can write down here beta 0 and this x bar, and this quantity is nothing but your expected value of beta 1 hat minus beta 1, and this we have shown that this is nothing but beta 1. So, this becomes beta 1 minus beta 1, which is equal to here 0, and so I can write down that here expected value of beta 0 hat is beta 0. So, this beta 0 hat is also an unbiased estimator of beta 0. So, now I can define the bias of beta 1 hat as a expected value of beta 1 hat minus beta 1, which is equal to 0, and bias of beta 0 hat, that is expected value of beta 0 hat minus beta 0, that is equal to again 0. So, both beta 1 and say beta 1 hat and beta 0 hat, they turns out to be an unbiased estimator. So, next property is variance. Well, we have obtained the value of beta 0 and beta 1 using beta 0 hat and beta 1 hat, and we also have seen that both of them are unbiased estimator. Now, our next step is that we would like to know what about their variability. So, we try to find out the variances. Once we have obtained the value of beta 0 and beta 1 using beta 0 hat and beta 1 hat, and after that we have established that both of them are going to be an unbiased estimator. So, the next question is what about their variabilities? So, let us try to first find out the variance of beta 1 hat. Right. So, to make it more simple, I will try to express beta 1 has as summation I goes from 1 to n Ci yi, where your Ci was xi minus x bar upon sxx, right. So, you can see here this I can write down here summation I goes from 1 to n Ci square variance of yi and plus double summation I naught equal to j Ci Cj and covariance between yi and yj, right. Now I need to find out these terms. So let me try to find out this this variance of yi first. This is separately. So variance of yi is nothing but variance of beta 0 plus beta 1, say this xi plus epsilon I, right. So since I have assumed that beta 0 and beta 1 are non-stochastic and they are fixed values, and xi is also a fixed, it is not random. So this entire part, this becomes constant. So this variance expression becomes same as the variance of epsilon I, and we have assumed that the variance of epsilon I is sigma square. So the variance of yi also becomes sigma square. This is a very important result. Later on you will see that using this result we will try to establish and we will try to infer many statistical properties. What is the advantage? You had assumed that epsilon 1, epsilon 2, epsilon n are the random errors. They are unknown to us, that you cannot know what are their values, but we assume that they have got a variance sigma square. Now, in case of a real data set, you only get a value of xi and yi. You will never have a value of epsilon I, but your model depends on sigma square. So now, in case if you want to infer about sigma square on the basis of xi and yi, this result will help us at that place. So variance of yi and variance of epsilon I, they are the same. And now the question, next question is, what is the covariance between yi and yj? Right. So this I can write, this is 0. Why? Because we have assumed that epsilon i's are independent. So once epsilon i's are independent, so yi's are also independent. Right. So I can write down that the covariance between yi and yj is 0. So this variance of beta 1 hat, this becomes here simply summation I goes from 1 to n ci square times here sigma square. So let us try to simplify this expression further. So I can write down sigma square summation I goes from 1 to n. This is xi minus x bar whole square upon sxx square. So this is sigma square sxx upon sxx square. So this is nothing but your sigma square upon sxx. So this is the variance of beta 1 hat. The next question is that, well, this is depending on sigma square. Sigma square is the population variance. Again, that is unknown to us. So how to know it? On the basis of given sample of data, right? So that we will try to address in the coming slides. But before that, we try to find out now the variance of beta 0 hat, right. So variance of beta 0 hat is nothing but variance of y bar minus beta 1 hat x bar. So this I can write down here using the simple statistical rules, variance of y bar plus x bar square variance of beta 1 hat minus twice of x bar covariance between y bar hat and beta 1 hat, right. So now let us try to find out these expressions one by one. So what about here variance of y bar? Variance of y bar is, we have assumed that each observation yi has got the variance sigma square. So this becomes variance of 1 over n summation I goes from 1 to n yi, and this is pure sigma square by n, right. Okay. And what about this covariance of y bar and say beta 1 hat? right. This can be written as a expected value of y bar minus expected value of y bar and beta 1 hat minus expected value of beta 1 hat, right. So, if you try to expand it, this becomes y bar minus expected value of y bar is epsilon bar and this beta 1 hat is I goes from 1 to n summation C I y I and expected value of beta 1 hat we already had obtained beta 1, right. So, again if you try to substitute here the value of beta 0 plus beta 1 say here x I plus epsilon I, and if you try to simply open it and then take the expectation using the property that expected value of epsilon is equal to 0, it will turn out to be 0, right. So, I can write down now here that the variance of beta 0 hat is variance of y bar from here, this is sigma square by n plus x bar square and variance of beta 1 hat that we already had obtained, right. So, this I can write down here as a sigma square over sxx and minus this quantity, that is twice of x bar into 0. So, this comes out to be sigma square 1 over n plus x bar square over sxx. So, this is the variance of beta 0 hat, but again you will see that that this is depending on the quantity sigma square, and again sigma square is the population variance that is unknown to us in practice. So, yeah, how to estimate it, that will be our next question. But before that we have obtained the mean and variance of beta 0 hat and beta 1 hat. So, let us try to find out also the covariance between beta 0 hat and say beta 1 hat. That will help us in establishing some more statistical properties later on. So, if you try to see, this can be written as covariance between y bar beta 1 hat minus x bar variance of beta 1 hat. Actually, that will be covariance between beta 1 hat and beta 1 hat, which is nothing but your variance of beta 1 hat. This expression we already had obtained in the earlier slide, this comes out to be 0, and this we already had obtained, that variance of beta 1, this is nothing but your sigma square over sxx. So, you can see here very clearly that this is minus x bar sigma square upon sxx, and this quantity is not going to be 0 in general, and that is expected. So, do not assume that what we have obtained beta 0 hat and beta 1 hat, they are independent. No, under usual circumstances they are not going to be independent unless and until either x bar becomes 0 or sigma square becomes 0, right. So, there is another thing, that we have obtained the value of beta 1 as beta 1 hat, which is sxy upon sxx, and we had obtained the value of beta 0 hat as a y bar minus beta 1 hat x bar, right. Actually, I can show that they are the best linear unbiased estimator, which means this beta 1 hat is the best linear unbiased estimator of beta 1 and beta 0 hat is the best linear unbiased estimator of beta 0. Okay. But after this he would like to investigate some properties of the model based on the values of beta 0 hat and beta 1 hat. So, one important property that can be observed from here is the following. Right, we had got the model which was beta 0 plus beta 1 xi plus epsilon I, this was our model, and we had obtained the fitted model as a like this. fitted model. And based on that, we had obtained the fitted values for a given value of x and xi. So, when I try to define my residual as say yi minus yi hat, let us try to see what happens to summation epsilon I hat. So, when I try to find out the summation of epsilon I hat here, this becomes summation yi minus yi hat, right, and this is nothing but your summation I goes from 1 to n yi minus beta 0 hat minus beta 1 hat xi, right. Now, what is this value? Means I would write it this is equal to 0, but how? It does not look like, right. But if you try to recall, when we had obtained the normal equation after differentiating the function s beta 0 beta 1 hat, so from the normal equation that you had obtained here, right, you can see here that this summation yi minus beta 0 minus beta 1 xi is equal to 0. And now, what are your beta 0 and beta 1? They are the solution of these two equations, this equation and this equation. So, I can also write that yi minus summation beta 0 hat minus beta 1 hat xi equal to 0, and similarly I can also write that some yi minus beta 0 hat minus beta 1 xi times xi is equal to 0. So, these are your two normal equation, they have been obtained at the time of obtaining the least square estimate. So, now using this equation I can write down here directly, because this is coming from the normal equation, right. So, you can see here what I am trying to say in this result is that the sum of residuals is 0. Now, here you have to be a little bit cautious. When I make an assumption that expected value of epsilon I is equal to 0, then sometimes people get confused with the same result. But you have to keep in mind that when I say expected value of epsilon I is equal to 0, that means I am saying that the average of the random errors in the entire population is 0. But here I am trying to say that we have got a small sample, we have got n data sets, based on that we have obtained the residuals, and now I am trying to show that the sum of those residual is also 0, and in turn the sample mean of residual will also be 0. Sometimes people get confused that what is the difference between saying epsilon bar or the sample mean of epsilon is 0 or the population mean of epsilon is 0. So, here you have to be little bit careful, right. Next result which I would like to inform you is that the fitted regression line passes through the centroid. Centroid is what here? In our case, the centroid is x bar and y bar of the data, right. That you can actually verify. If you try to substitute the values of x bar or y bar, you can easily verify it. The next result which I want to show you is that summation xi epsilon I hat is equal to 0, right. I goes from 1 to n. So, now exactly using the same technique which I used in demonstrating the earlier result, I can also do the same thing here. This is xi, this is yi minus beta 0 hat minus beta 1 hat xi, right. Now, how I can write that this value is 0? So, if you come here again on this slide, using this result, the result based on the second normal equation. This is simply saying that the summation of yi minus beta 0 hat minus beta 1 hat xi times xi is equal to 0. So without doing here much, means I can write down this value to be 0 using normal equation. Right. Which normal equation? That del beta 0 beta 1 with respect to beta 1 is equal to 0. Right. Similarly, it is not difficult to prove that I goes from 1 to n yi hat epsilon I hat is equal to 0. So, these are some simple properties that we will use later on in establishing some more statistical properties of the estimators, right. So, now we have considered the estimation of beta 0 and say beta 1, and we have investigated their statistical properties. One thing is still left, how to estimate the sigma square. That is a parameter that is still remaining for us. So, now we stop here in this lecture, and in the next lecture we will try to estimate the remaining parameter sigma square. Till then, goodbye.